So we're discussing columns. And more importantly, we're discussing the stationary phase that's on the inside of these columns, right? So we've talked about the stationary phase, and we've talked about these little prongs that are sticking out that are really functional groups. And the purpose of those prongs or those fingers is to slow down the anions or the cations that are making them way through. All right. So the first thing that I want to say is, how on earth does this interaction really take place? What's going on chemistry-wise? What's the details that are happening on the inside? Well, first, what you need to keep in mind is that these are all playing off of charges, negatives and positives, and how they're interacting with each other. So we are often calling these interactions dipolar interactions. And you can kind of see why we're calling that. Di means two, and polar means charge. So how are these charges interacting with each other? We've got one on the stationary phase, and we have one in our mobile phase that we're trying to separate from the rest of the group. So how are they interacting, and what are they doing on the inside? What you're going to find out is that the stronger the interaction, the longer the retention time. That kind of makes sense, right? So if I've got a particle that comes into the picture, and that particle makes its way to the stationary phase, and it stays here for quite some time, maybe like in-laws coming into your house and staying there for weeks at a time before they leave, this is going to cause some retainment in the system, right? They're going to be there a little bit longer. They have no hurry of ever getting out, and you're just going to have to coax them a little bit more and more and more with extra mobile phase in order to push them along and go on out the door so they can go on back to where they came from, right? They can go on back to their own house. All right, so the same thing's happening here with the interaction between the analyte of interest and the stationary phase particle. The stronger the interaction, the more the analyte will be retained. Most of the time, the retention time is going to be determined by charges first. Now, not every single time. All right, I am oversimplifying this whole interaction. So if I'm looking at the way things elute, most of the time, the positive or negative ones will come off first, and then the positive or negative twos will come off second, and then the positive or negative threes will come off third. Now, it doesn't happen this way every single time. It also doesn't happen this way on a general run-of-the-mill group or family that we're talking about. There's always exceptions to the rule. But if I had to oversimplify it and give you an idea of order of elution, then this basically is kind of the number one thing that we can talk about. But charge is not the only thing that we have to worry with. So the number two thing that I always have to worry with these interactions is the size of the analyte. The size of the analyte's pretty important. Typically, small ones come off first, and then we get our medium-sized ones that come off second, and then we get our big-time large ones coming off third. So two things are really into the picture, and they're playing off of the same thing at the same time. Order of elution or retention time is based on charges, and it's based on sizes. All right, so let me give you an example. Let's say that we get a chromatogram and we get something that looks like this. And let's say that I have injected fluoride, bromide, and chloride into the system. And I've been lazy and I have not injected standards to get retention times. And I should be, right? I should be injecting fluoride to get the retention time of fluoride. And then if I have a combination like this one, I will just match the retention times up and I know which one's which. The same thing would happen with bromide and chloride. I would inject standards of just those, get those retention times, and then in a combination chromatogram, just match them up, and that will tell me which peak is which. If I had to make a best guess, though, typically what will happen is that I will go and take a look at charges first. All right, so fluoride is a -1, and bromide is a -1, and chloride is a -1. These are homologs. That basically means that they all belong to the same group of charges. They're all -1 here. So number 1 is not going to break it for me. Okay, the number 1, they're all the same charges, so I need something else to go by. We know that these 3 things can be separated, but it's not going to be based on charge because they always have the same one. So now we take a look at sizes. Which one's smaller? Because that's probably going to come off first. Well, if you take a look at the periodic chart, in Chemistry 151, hopefully, you learned about a periodic trend. And the periodic trend is that as you go down the periodic chart, your atoms end up getting bigger and bigger and bigger. Okay? So if you take a look at the halogen, you'll see fluoride up here at the top, and then chloride down below, then bromide down below that one. All right, so that probably means that fluoride will come off first in the chromatogram, and chloride will come off second in the chromatogram, and then bromide will come off third in the chromatogram. And if you take a look at a traditional setup of the IC system, that's exactly what you're going to find out. All right, so as long as they're the same charges, then you can kind of go with the sizes of the analytes in order to figure out which one's going to come off first, which one's going to come off second, which one's going to come off third. The problem here is that when we start mixing everything up on you, all right? So let's say that we've got fluoride and chloride, and let's say we have iodide this time, and then we have nitrate, and then we have maybe sulfate, all right? So sulfate's a -2, nitrate's a -1, iodide's a -1, chloride's a -1, fluoride's a -1. So let's say that we get a chromatogram. There's 1, 2, 3, 4, 5. So here's my first one, second one, third one, fourth one, and fifth one. Now we want to kind of figure out, well, what's going on, right? Which one's going to come off first? Which one's going to come off second? Well, if you go by these rules, and remember, I said these rules are oversimplified and general stated, then I would probably group all of my -1s together first. So fluoride, chloride, iodide, nitrate, sulfate. So you're probably looking and saying, all right, well, here's my -1s. So the smallest one here is fluoride, and then chloride kind of opens up, and then I get this iodide, and then I get the nitrate. So which one's going to come off next? Remember, smaller ones come off first. So this N and the O3, I mean, that 16 times 3 plus another 14, is that bigger than the iodide? Not really. So you probably would want to put NO3 here and then I there. And then sulfate's a -2, so sulfate will come off last, right? So the answer is you almost have it here. Almost, but not quite. Because if these rules were set in stone, then yes, this probably is how they would come off. The problem, though, is that both of these really are determining factors at the same time. Meaning I should be looking at charges and I should be looking at sizes both at the same time to determine the point of elution. You've got the fluoride correct. You've got the chloride correct, and you've got the nitrate correct. However, what you're going to find out is that the sulfate would actually come off before the iodide. So SO4 here with that -2 is going to come off before the iodide does in the very end. Again, it's all about the sizes. It's taking that iodide a little bit longer just to push itself through that mobile phase or that stationary phase versus something like sulfate. Even though sulfate has a -2 charge, it can kind of maneuver through there a little bit better than the iodide can. So what I'll try to do on the test and the assignments and stuff is give you very simplified versions that make logical sense. Whether or not that's actually how it really happens in real life, that's something that you have to do experimentally sometimes. You got to kind of run standards, see with the retention times. It's not as straightforward as boiling point with gas chromatography. Even with boiling point, what you saw is that sometimes the polarity outweighed the boiling point, especially if they were really close in boiling point. Same thing happens here. We always get exceptions, and those exceptions are going to cause us problems sometimes if we're not expecting them or if we don't see them coming. All right. Notice that I keep talking about hanging out, right? These things are hanging out with each other. What that really is referring to is equilibrium. And if you've taken a Chemistry 152 class, you kind of know what equilibrium is. What you've talked about during that time is the concentration of the products over the concentration of the reactants. And you can take these concentrations and divide them and get a K, which is what we call the equilibrium constant. So all analytes, they're all different. They all will have their own K equilibriums, meaning they have their own equilibrium constant where sometimes they're hanging out with the stationary phase and sometimes they're hanging out with the mobile phase. So this means that they are spending longer amounts of time on the surface of the stationary phase. So as I draw the stationary phase, I have this particle that's going to come in here, and this particle, let's say the red one, is going to stay on the surface of this particle much, much longer. Well, let's say that a second analyte comes through, and that also stays on the surface of the particle, but I'm going to see some of that kind of staying off in the mobile phase too. It doesn't stay as long on the surface of that thing. Because of that, we get natural separation that begins to happen. The K equilibriums, this whole hangout idea, can often be modified by playing around with pH. So this is why it's very important sometimes for pH to be controlled in your mobile phase and inside of your columns and inside of your samples. pH is going to be a determining factor on how things will hang out on the surface of that stationary phase. So keep in mind, if your in-laws came around and they wanted to stay for a long period of time, you need to switch up their equilibrium. You need to switch up how inviting your home is going to be. If you can change up the pH and make your house disgusting and filthy and roach infested, then your in-laws probably are not going to stay that long. So they're going to come, they're going to visit, but poof, they're out the door. Versus if you have a house that's pristine and clean and it smells good and the sheets are fresh, those in-laws are going to stay a little bit longer. So their KEQs are going to be affected. So this is why pH is often very important on chromatography, and it's not uncommon for you to read directions that say you want to check the pH of your mobile phases and you want to check the pH of your samples. You kind of want to bring them to a certain value before you do anything at all with them, and if so, then this is one of the reasons. You're just controlling how long they retain onto the surface of that particular column. Okay? Something else that we want to talk about is that your capacity of your home is going to be a little bit different depending on what size home that you have, right? So we now want to bring in this concept of capacity. So all columns have capacity, and different columns will have different capacities. So for instance, you have a house or you have an apartment that you're living in, and that has a certain capacity. You might have one bedroom, you might have two bedrooms, you might have five bedrooms. Who knows what you've got? But you will have a specific capacity of how many people can spend the night with you at one time. The same thing is going to happen in columns. Columns have capacity. And the capacity here for a column is not the number of bedrooms. The capacity here for a column is the number of what we call ion exchange groups. And these are typically not listed in a catalog. All right, it's typically not listed by a manufacturer. It's just something that the manufacturers will know, but it's not information that they will stamp into a booklet for you to order from. It's important, but not that important to waste the time and stamp it on the inside of the books. If you want to know more about it, you call them up and you ask them. They'll get you in touch with one of their chemists, and they'll tell you kind of a little bit more that what you need to know about it. But the ion exchange groups is basically the particle and how many prongs are coming off of it, right? So here we've got one that's got 4, and then here I can load this one down with more prongs, and what you'll see is that as a analyte comes in, it kind of gravitates toward one of these groups that are charged, and it hangs out there for a while. Well, this one's got 4 bedrooms, so it can hold a certain amount. Well, this particle, it's got more bedrooms, so this one can hold more amount of analyte, and this is what we would call a capacity of our column. That all depends on how many charged bearing groups I have on the surface of that particle. So, capacity is determined by the number of ion exchange groups that's on that stationary phase. This also is going to determine retention time, right? If I've got a column that has these particles and they are loaded down on the outside, then it can welcome more sample and it can hold it a little bit longer versus a stationary phase that maybe only has 4 bedrooms to share. Well, if these things are all loaded down, then this particle or analyte that's coming into the picture, it's got nowhere to go. So it's not going to get held behind. And it just kind of zooms off and it moves off to the next particle that might be down here toward the bottom. So they're going to move through the column a little bit faster if the capacity is very low. All right? So retention time is affected by capacity, because if they run out of spaces to stay in, they have to just keep driving along the interstate until they find a vacancy at a hotel that they can pull off and stay in, right? Something else with capacity is that a high capacity, meaning a particle with a bunch of bedrooms that can house a lot of analyte, will typically need a strong eluent in order to wash everything off of that particle. It's loaded down, right? And sometimes these particles get a little too comfortable and you want them to go. And the way that we do that is if we increase the eluent pH and we put a stronger concentration of eluent in our mobile phase, then we're going to go through and we're going to have to pump that stronger solution through so we can dislodge all of those particles that are stuck to the surface. A low capacity column, well, they don't have as many bedrooms, so no vacancy is going to start popping up a little bit more often, and this is going to lead to what we could call a column overload. And a column overload basically means you have too much analyte or sample that you have injected into the column. What happens is that when you've injected that sample in, all of the bedrooms get filled up immediately, and then you still have sample left over, and that analyte has nowhere to go. So it's completely filled up. And what will happen is that this sample gets injected, and all of these components will go right through the column. They'll get no retainment at all. And that's because there's nowhere for them to go. All of these sticky fingers that are sticking up off of these particles, they're all taken. And because they're all taken, because they have nowhere to go, they have nowhere to go but through the column and out. So your retention or your retention times begin to get modified, and you might see weird things that happen in your chromatograms because of that. So low capacities are going to be a problem. You need to be very careful with the amount of sample that you pump into those columns if they have low capacities, right? We talked about anions and cations, right? So as far as cations go, cations are really non-suppressed. Remember, we can have anions that are non-suppressed as well. It's not common, but we can use them. But anything that does not require a suppressor, these columns, general run-of-the-mill columns, have low capacities. So if you're injecting cations and you're looking at positive pieces that come through, you have more of a danger of saturating those vacancies in that particular type of column, and these cations will zoom right through and out the other end. So sometimes it's harder to separate the cations based on that, especially if you overload the column with too much sample, or too high of a concentration of sample will also give you the same thing, right? Higher concentrations lead to column overload. There's too much stuff that's present for them to separate and give you a very good signal. So that's what we're calling the capacity of the column. So in the next video, we'll continue on with this discussion of capacity. We'll talk about it a little bit more, and that way you're a little more comfortable with it.